right, so I think it's time to start our session. We are going to talk today about the restoration of the Xerox Alto that we did. So that I'm Marc Verdiell, and my co-restorer are Luca Severini, Claunch, and Ken Shirriff. We're going to try to go through it at a good pace and launch right into a demo afterwards. So we're going to tell you a little bit of the story of our restoration. Before I start, I wanted to put a slide in memory of Ron Crane, which we hope to have on the panel with us today, but unfortunately that was not possible. He passed away a few weeks ago. He was an Ethernet pioneer, so you owe him the Ethernet and the Internet, or part of it, co-founder of 3Com and a fellow restorer at the museum and on the Alto. So first question is why restore an Alto, and the simple answer is because it's an awesome machine. It's a research machine that was developed at Xerox PARC starting in 1973. PARC stands for Palo Alto Research Center, right in our backyard, and we are going to have some of the Xerox PARC alumni, the people that actually made the machine and the software on the machine, have a session just after the demo, so stay around. And that machine just is very early in 1973, so it's a TTL machine, but it demonstrated a mind-boggling list of innovations, mostly recognizable by the bitmap portrait screen, the first machine with a GUI with mouse. We even have the optical mouse that was made by Dick Lyon, and Dick is here with us today. First optical mouse, of course. No windows and menus, the WYSIWYG text editor, that's awesome. Ethernet was invented for that machine. Laser printing, object-oriented programming, you name it. Everything that is we take for granted in a modern computer is already in that machine. 10 years ahead. And famously, this machine inspired, or is said to have inspired Steve Jobs in his visit in 1979, and it'll become obvious to you why when we fire it up. So it's really the ancestor of our modern personal computer. So the Alto is fairly rare. There were only 2,000 made. It was never commercialized. This was a research machine. Ours come from the Y Combinator. It's a VC firm in the Valley that funds mostly software companies. And it was donated by Alan Kay, a famous Xerox PARC researcher. And you see him there holding his Dynabook concept, which looks suspiciously like today's tablet. Now, at the time, you could not build a Dynabook, obviously, in 1973, but the Alto was to be the interim Dynabook to demonstrate all of Alan's very visionary concepts at the time. And that's the Alto as we saw it the first time at the Y Combinator. And actually, in the frame, there's Ron Crane, who passed away, and David Box, his good friend. Also, two Ethernet pioneers, and that was how we saw the display first. So it was in pieces, but it seemed to be complete. And so they asked for a team to restore it, and we volunteered. We all know each other from the Computer History Museum. We work on the 1401, it's on our badges. And I happen to have a little bit of a dream setup at my place to restore computers. So welcome to my basement. This is my collection of HP test equipment. So if you have something to test, I probably have the right piece of equipment for it. This is my workshop. I have a mill and a lathe, and when I don't use them to make parts for the 1401 or other computers, it's very useful to make R2D2s. And I have also a collection of computers, mostly HP, but quite a few parts, and we digged into those for the restoration. So it was quite natural for the machine to come to my luxurious basement. And that's how the setup looked like. the screen all the way to the right, the guts of the machine just slide out, and you see them next to logic analyzer to the left. What else? There's a rig for testing power supplies. We had the original disk and an extra disk. And to the far right, or left for you guys, is the logic analyzer. And you'll see that this would have become our principal means of debugging and restoring the machine. Right. So all good restoration starts with power supply debugging, and ours was no exception. The Alto has the power supplies at the back of the chassis, has 4 of them. They do a whole bunch of voltages. And surprisingly enough, we only had one bad, which was the plus 15 volts. So that was no easy peasy lemon squeezy. It's a Sorensen supplier, a switcher, very nice. They went for high-end supplies, professional. And I'm sure, who has had a bad capacitor in a supply? Yes, okay, well, it happens quite frequently. So we went straight for the caps. Sure enough, the big silver one, the 1,000 microfarad, showed 25, so that was no good. So we put the 2 blues in there. And notice that there's other capacitors, actually, of even bigger capacitance next to it. We didn't change them. We only changed the ones that we find are failing, and we try to leave all the original parts in it, so we never do a complete recap. So off with the power supply. That was easy. Monitor restoration. So the monitor is actually a commercial TV monitor, and the Xerox people told us that they went around with a sheet of paper and found one that had the right aspect ratio because they wanted to do office publishing, right? Xerox, copier company. So great news, it's commercial, it's just slightly modified for the rate, so the schematics are available. It's weird because it doesn't come up until you give it sync in both vertical and horizontal. Fortunately, the Living Computer Museum had gone through a restoration, they had made a tester. Thank you, Josh, are you here? Yes, from the Computer Museum back there. You'll see a lot of help from them. So that's the little contraption you see. We hook it up and no image whatsoever. So that's the interior of the ball monitor. Looks like a TV monitor because that's what it is. And as I told you, the schematics are available, so it's not too difficult. We soon found out that it's in the video section that wasn't working right, and we replaced whatever C130, another electrolytic, and a bad pot. And at the end of the day, we started to get an image. You see on the left those 2 bars. That's what the tester is supposed to show, but they were very, very dim, and that got us concerned. By the way, this is the number of the tube. So obviously the tube is at the end of its life. And we looked for one, couldn't find any. Number is right there. If you have one in your drawer, we would like to know about it. Good news, though, is that after we left the filament on for a week or 2, it brightened considerably and became useful enough. And that's what we have today. So what happened is that probably the contaminants boiled off the cathode. So we didn't have to do anything nasty to the tube, like rejuvenate it, which is only temporary anyhow. So it's holding up. The disk, which we need for booting, of course, becomes our next focus. It's a Diablo drive. It has these big cartridges. We'll show them to you later. There's one sitting on top of the Alto. 2.5 megabytes, which is okay, but not so much, so we swap cartridges often. Slightly modified, again, for timing. So the main concern bringing those drive, you probably know, is cleanliness, because if you get anything, those cartridges are open, and also there's air blowing on it. If you need any piece of dust, you'll get a head crash and a disk crash, and you'll render both your disk and your drive unusable in one fell swoop. So clean the heads. We're lucky, those were fairly clean. Clean the platter, so every platter we receive, we open it up, we clean it. Ours had no gouges, was very good, so Carl, the specialist of discs. And the problem we encountered was another problem. How many of you have had foam problems in your old gear, right? So We got hit, of course, by the crumbling foam in the filter, easy enough to change. And we had a problem with a gasket that turned into goop, and so we rebuilt the gasket and make sure everything was clean. But otherwise, the disk was fine. We tested it with a tool that Carl made. He's an FPGA specialist. I'll talk later about that. Looked fine. So we are on to the Alto guts. That's a typical card of an Alto. It has about 13 of those. All TTL, no sign of microprocessor anywhere. We cleaned them all up, and that's where we hit our first major snag. You can't quite see it in the picture, but all the way at the top, it says Alto 2 Trident disk interface. And we have a Diablo disk. The Trident disk is a later, much bigger disk. So we are starting to get concerned. A, we don't have the right card. We can't boot it up. And B, we have this deep sinking feeling. Maybe this Alto never worked in the configuration we have it. And you'll see that that was indeed the case. So what do? I remember Ken proposing we go to Fry's and exchange it. But obviously, we can't do that. So we were stuck for a while, and we get saved by the CHM, by Al Cosso of BitSavers fame, who also happens to be a large collector of Altos and had a pile of parts that he collected just for situations like these. So miraculously, our Trident card gets turned into a Diablo card, and we are ready for the first power-up. And so you see the system. We kept it like this with the guts out all the way through restoration. So no smoke. We did a good job with the power supply. There was no major problems with electronics. Display comes up white. That was the first good sign because it means the sync is going, right? The display doesn't come up unless there's sync signal. The disk spins, the head loads, the ready lights come on, and Luca, I think that's your finger on the red button, right? So to boot it, you press the red button at the back of the keyboard, and nothing happens, right? Which was not unexpected, right? So now the tougher part of the restoration begins. So we have to understand how the Alto works, and before I go to the next step, I'll try to get you through the Alto's architecture in a few words here. So the Alto is a microprogram 16-bit CPU working at 5.88 megahertz, implemented in TTL, as I told already. So it's 74S series in the Alto 2. It has, for the time, an ocean of memory, 512 kilowords, and that's a 16-bit machine, so it's a megabyte machine. I can't think what it cost at the time to fill a machine with that much memory. And not only it does have that, but it also has microprogram ROM and RAM. And you'll see that this is very important in that machine. And the 2 kilowords of control ROM and up to 3 kilowords of control RAM, 32-bit instructions. So what's very unique about that machine is that it constantly switches between 16 microprograms, and the switching is done at hardware level. And those are called tasks. And what that does is that depending on which task it's on, this generic CPU will have a different personality. For example, the user interacts with the CPU when it's in task 0. And task 0 is a microprogram that emulates a Nova processor. So for the user, all he sees is a machine that looks like a Nova and executes instruction from ran one at a time, and in the background, the microprogram emulates Nova instructions. And of course, the reason that was done is that Nova was very popular at that time, no Data General mini computer, and Parc had done some work on it and wanted to reuse the software they had done and the development infrastructure. So, more about the micro tasks. So here they are. So we talked about task 0 at the top, our emulator. That runs when no other tasks runs, right? So that's the default. When it has nothing else to do, the Alto actually executes your program. Then you can see there's a few unused ones. The next one is task 4. And what is that one? The disk. It's a disk task. So there's a bit sector pulse. All of a sudden, the microprogram swaps. The CPU becomes a disk controller for a while and takes care of the sector. The next one is Ethernet, right? So same thing. An Ethernet word comes in. The microcontroller becomes an Ethernet controller. The CPU becomes an Ethernet controller. The next one is even more amazing. Is MRT, memory refresh task. So every 38 microseconds, the CPU becomes a memory controller and refreshes the memory, and so far and so on for the display, the cursor, etc. So what they did is very clever. They went around this problem that at the time they didn't have any microcontroller chip available to run their fancy new hardware. So instead, they use a generic CPU, very flexible because it's microprogram, and then they just microprogram it on the fly. They swap the microprogram on the fly, so it becomes a specialized controller for whatever it has to do in the machine. I find it extremely elegant, but it's also pretty hard to debug. Because the problem is that if the CPU doesn't run its microtasks, then nothing runs at all. I mean, nothing. No display, no disk, and you lose your memory because it's not refreshed, so you don't have even RAM. So it didn't boot, and we were very afraid our CPU was dead. So the first thing we went to figure out is, does it switch tasks? And the diagram is the control circuit for the CPU, and it has a little counter. It has actually 16 microprogram counters. So what it just does, it switches to the microcounter it uses, and off it goes doing the other task. So we went right for looking at those 4 lines over here, which is the currently executing task number on 4 bits, right? And that should wiggle. That should change. And you can do that with a simple scope. And as the first figure we saw, and we breathe a large sigh of relief, you can see the tasks. So they are active low. Most of the time it's at 0. It's doing the Nova emulator. No, right now it's doing nothing. Right? They have no program loaded. It hasn't booted. But you can count the bits, and one, I think, is a cursor task, and the next one is the memory refresh, the big red one, so it's 8. So, yay, the CPU is fine. The other thing is that it must run a lot of microcode properly, because this is not cooperative. The task has to relinquish its microprogram to do it. So it must run most of the micro instructions properly at this point. So the boot failure is something more involved. So here comes the logic analyzer. So it's, of course, one from my collection. It's an HP 1670G, which has 178 channels, which you might think is a lot, but turn out we use them approximately all. So that ends up in this big mess of wires. We had this in front of the Alto, probably an equivalent number in the front on the cards we were probing. And here's a typical trace that we get out. And it's basically numbers. And we never use a reverse microassembler or anything. We were mostly looking at the C-ROM address, so where it was in the ROM, the task number, and sometime at the macro instruction itself and data. And we followed along because we have the source code, and more importantly, we have Josh's emulator back there, which emulates down to the microcode. So we could see how it executes normally and compare to ours, and also map the instruction to the source code, because they're in random order, semi-random order, the micro instructions. So it's fairly hard to read, but Ken became a master at it. And we finally read them well enough that we can discover that the disk sector task never wakes up, right? It never wakes up because the hardware never wakes it up. So we go straight to oscilloscope probing and start to trace the logic from, so there's a line, there's 16 lines, right? Each of them you pull it and it's supposed to switch the task for you, try to wake it up. And we follow it backwards with the oscilloscope. There's quite a bit of logic between the CPU task wake up and the sector pulse he sees from the disk. And sure enough, is the last gate we probe. It's a simple inverter, the one at bottom, and the signal doesn't make it through. So one single inverter not working, fortunately easy to fix. We didn't have another circuit, but it was a free gate on the other side, so we make a hack. We rewire the gate that's not working to the gate that's working, and ta-da, our sector task now wakes up. So we're ready for boot trial number 2 with a working sector task. And no cigar, of course, doesn't boot. But we can see on the logic analyzer it goes much further, and in particular, now it read the disk and read the whole first sector, which it's supposed to do. And then, no, why didn't boot, why couldn't it execute? We look at the data, because we can sniff that with the analyzer, and it's not even Nova code that's on our disk. In fact, it's pseudo-random data, and Ken, which is the master of reading row numbers, was able to match it with the disk test program from which we had the source code. So it's pseudo-random data from the disk exerciser from the Alto, proves it. So now we figure out, we put A and B together. There was disk, on our disk, there was this tag, it's still there. And it says, if you can read it in red, drive was realigned on July 21st, 1986. And what probably happened is that at the end of this realignment, they ran the test program and it erased our disk with random data. So we don't have a boot disk. We need a new old boot disk. And we get saved by the LCM, again, the Living Computer Museum in Seattle. George makes a new old boot disk on their restored Alto. And sends it to us in original box, right? Old foam. And we put it in, and still no boot. So darn. Back to the LA, and we soon figure out that it's reading cylinder 8 instead of reading cylinder 0. So it got the wrong sector from the right disk. So that must be a hardware fault, and we think we quickly focus on the disk, it's fine. Then we look at the cable, and it's not fine. It has a nick in it. We repaired the nick. Boot trial with repair cable, and you can see from the picture at the right, it boots. And that's how we felt. And that was, to give you an idea of time, 5 months into the restoration, working on it, about together, a day, a week, and then doing the data analysis in the background. And then we're greeted by the command line, Xerox Alto Executive 12, and we have Alto number 103. That's its address on the Ethernet, which has all of 256 addresses, right? It's on 8 bits. So we have machine 103. Yoo-hoo! So the yoo-hoo lasts a little bit, but not very long, because we get that screen, and that's the debugger screen. And every time we try to run something interesting, it crashes, either or in the debug screen, which is called SWAT. So something is more wrong than we thought. Again, logic analyzer, the difficulty here was to remember to trigger, right? And so now it's running most of the time, so it's spewing data out, and you have to kind of make sure you capture it at a crash point. We managed to do that, and we figure out it jumps always at the same place, which is good. So it crashes at the jump RAM assembly instruction. And that happens to be an instruction that is not a Nova instruction. It's a specific instruction for the Alto, and what that does, it allows the user to jump to its own portion of microcode that he wrote in CRAM. Why would you do that? Because you're programming assembly, that very high level language, and that's not fast enough for you. So therefore, you want to optimize further in microcode, right? So what that does, usually the microcode is run from ROM, and there's some logic that switches it out from another processor to RAM, so it switches to RAM. So we focus on that circuit pretty quickly and try to debug the bank selection, which is on the card, and that's too complicated to do with an oscilloscope, so we do it with a logic analyzer again. So we figure is the switch mode microinstruction that doesn't work, and that the Alto never switches to CRAM. It continues executing at the wrong address in CROM. It's another of Ken reading the microcode. And then, no, this time we're much smarter. We debug starting from the left, going to the right, Because we got taken last time. And sure enough, the fault is way at the end. And it's this circuit there, the circuit, the pulse doesn't come out. So you see it in yellow, it comes in. Green comes out, so it stays in ROM, never switches to RAM. We replace the circuit, I happen to have one, and the same failure happens. Nothing changed. Then we start to smell that something is wrong here. We do the same test, but we lift the output pin from the socket. And sure enough, now you have the green pulse coming out. So the circuit was fine, but there's something wrong with the circuitry that grounds it, and it's the if you have ever debugged a ground in a logic, that's the worst, right? Where is it going to, how do you find a ground? Could be anything where this is connected to. However, in our case, it wasn't that hard to find, so we take the board out to figure out what the traces are at the back. And sure enough, on our pin, there's an extra white wire, and our card has been modded. And what happened is that the mod, this wire, grounded the pin in a really roundabout way. It moves the pin to the edge connector. The edge connector has a cable that goes so that the control RAM board, it goes to the control RAM board, and the control RAM board grounds it. So do we have a bad control RAM board? No. It turns out we have a good control RAM board, but we have the wrong wine pairing. So go back to the manuals. There have been several versions of control RAM, control ROM. They started at 1K, they moved, so they have, and you need to upgrade them in pairs. So we had the 1K board that was modded to support the 3K RAM board, but our RAM board is 1K, so we don't have a valid combination, and our Alto could have never worked properly. It's really a pile of parts. So we go to our usual provider of cars, Alcoso. We get, so he give us like 8 boards. Right? So we find a combination that works, and ta-da! Now everything works. And we have these little icons, and we reach for the mouse, so we need to get our mouse working to use the programs. But that's where we say, "Oof, we're really over the hill here. It's not crashing anymore." So mouse. From Dick Lyon, we have the optical one. It's now signed by Dick. I hope you can show that. So it's an amazing piece of hardware. Simple Fault does not even get power. Why? Because we discover the connector is a PC connector, which has been modified. It's a 9-pin PC connector. And the Alto has a DE19, which is exactly, so they fit into each other, no problem, but no pin makes contact ever, right? So it's not because you have two things that fit into each other that they had made for each other. So finally, we mod it back to what it should be, and the Alto it up, and it's awesome, and we're going to demo it in a minute. I am right on time. So we have draw, we have Bravo, we have pinball, and you'll see them all in a second. So, looking back at what happened, what had failed? Well, in retrospect, not that much, right? We had the supply caps, the monitor stuff, the foam in the disk drive. You see we'll have another problem with it later on. And only one gate in one IC in a board that was a spare, obviously, probably for that reason. So, no, all in all, pretty good. And no, most of our issues because we had the wrong parts in our machine, right? We had the wrong disk interface, the wrong boot disk, the CROM card is not made to work with the CRAM, and the mouse with the wrong connector. And also, I skipped over a lot of details, but what took also a lot of time was the tool development. And I'll show you an example of the tools we had to make in here. Task Explorer that was used to find out that the task was not running, so we feed it. That was made by Ken. We feed it a microcode trace, and it figures out what the Alto is doing. And you can see it's mostly trying to do Nova code, and then you have the sector task. So that's after we repair the disk, right? So that's the hooray trace. The sector tasks works, and it reads word from the disk at the bottom. So that's one software tool. Hardware tool, that's the FPGA disk tool made by Carl, and that allows us to work with our extra disk, and we can read disks to a PC and write new disks. Very useful. It's also allowed us to debug our own disks. That took a long while because it's just not well documented, right? We had to scope, read the microcode, figure out what was going on. And finally, the Ethernet took the longest time. It's not standard Ethernet, pre-standard, 3 megabits. All the protocols are different. Kind of similar, but different, right? So Ken made a BeagleBone emulator of this, so we can, the Alto feels like it's connected to the Ethernet. It emulates the server facilities that were at Xerox. And it bridges to the modern Ethernet. And we're not going to run Ethernet now because our Wi-Fi is so flaky. So we can't run 1974 stuff because the 2017 is not so good. But the LCM has also done that, and we use that in our booth, so you can see some network booting. And it's never finished. That's our disk a few days ago when we were trying to make that demo, and the spindle failed. So we had to go change the ball bearing on the disk spindle. Okay, so happy ending. That's the email from Sam Altman, the top guy at the Y Combinator, saying that he was so awed by our restoration, which is on YouTube, by the way. Some of you might have seen it. I'm Curious Marc on YouTube. I chronicled it and say, okay. I consider the Alto rightfully yours at this point, so it's good to blog on YouTube, right? So, okay, special thanks. We couldn't have done it. We have had great support from the community. Sam Altman, of course, for giving us the machine. Xerox Park, Tim Curley gave us original documents. We are archiving disks for him. Living Computer Museum, Alcoso for the boards and the disks and the emulators. Bruce Damer from DigiBarn, we have his chord set over here. And Robert Garner for constant encouragement and bringing the Xerox, reaching to the Xerox people. And without further ado, Xerox live demo, and after that, the alumni panel. So for that, I'm going to switch and try to get my camera to project what's on the screen so you can all see it.
Hello? All right. Well,
another note before I start, we kind of wanted to defer the question to after the panel because we wanted to do half an hour of talk, but half an hour of demo. So we'll take questions afterwards when we have the whole panel with the original Xerox people.
all right, well, thank you everyone for coming out here. You've heard about our restoration. Now I'm going to show the system in operation. So first of all, I'm going to reboot the system by pushing the red button on the back of the keyboard. And now it's rebooting off the disk here. And now you might expect it will come up with some lovely user interface, but instead all you get is a command line. That when you initially boot the system, can you hear me? Okay, can you hear me? Okay. All right, I'm not sure if I can type and hold the mic at the same time, but we'll see how it goes. So from here we can...
Hold on a second here.
Okay.
I'm in focusing hell.
Okay, so what I did is I hit a question mark, and then it goes and lists all the files that are on the disk here. It was working just fine when we tested it earlier. You know, we have it just set up so we don't get the glare from over there. All right, well, you know, while we're waiting for the focus, I can talk a little bit about the hardware. We have the optical mouse here. This was invented at Xerox PARC. They invented the optical mouse. It has a special grid of dots that it uses with the sensor inside the mouse to pick up. It has a 4x4 sensor. How are we doing on the focus? There you go. We also have the cord key set over here that was used for some control operations, but turned out to be not as popular as the mouse. So that's why nowadays you see a mouse and you never see a cord key set. Are we there?
Well, that's the best I can do for now.
Oh.
Oh, I know it focuses on the reflection. Do this and do that. There you go.
Okay.
Feel comfortable?
Yeah.
There.
Okay. So what I showed here is a listing of the files on the 2.5 megabyte disk drive. You can get a nicer view of the files using the Neptune file browser. And so what Neptune gives you is much more of a graphical view. It's kind of like a Finder today. On the left, you have a list of files. You can click to select files, click with the mouse, and then if you have 2 disks, you can copy files onto the other drive. With the right button, you can select files that you want to delete. So it gives you a more graphical way of interacting with the file system. And then off on the left, there's this invisible scroll bar. You see if I move the mouse over here, it turns into an arrow. And now I can scroll through the list of files. So here's where they invented the scroll bar. Next, I'm going to move on to Bravo, which is the text editor. So Bravo was the first WYSIWYG text editor. It was developed at Xerox PARC by Butler Lampson and Charles Simoni. Simoni then went on to Microsoft and started Microsoft Word. So this editor is basically the parent of Microsoft Word. Now, it might not look too much from this point. It's just a status bar, and you use keyboard controls. So I type G to get a file, put in the file name, and now it will load this file. So as you can see, it gives you a very nice display. You have multiple fonts. You have justified text. It's justified on the left and right. You can center the text. It has a mathematics font you can see down here. It even has a smiley face in the font. So perhaps this was the world's first emoji. I'm not sure. To edit your file, you can use the mouse to select a region. You click to select the left and right of the text. It underlines a region that's selected. Now I hit L to change the look, and I can change it to a different font. So I can change it to any of the selected fonts. I can change it to bold, hit L and I to change it to italics. So you've got all the control over the way it looks that you might want. And then what Xerox did is they also invented the Ethernet and the laser printer, so they could hook up printers to the network, and then they could print out all their documentation. So the documentation for the Alto was designed using Bravo and the other systems, and then they could print it out and get a high-resolution documentation. So it was basically the origins of desktop publishing. So I'll load another file here. So on one of the disks, we found the original Bravo files for the hardware manual. So this is the actual hardware manual for the Xerox Alto. And again, we can use the invisible scroll bar and scroll through it. So really, Xerox was eating their own dog food. They were using these systems to build their documentation and other things. So let me quit out of here by hitting Q. Can you hear me okay with the microphone? Okay, good. And next I'm going to show you Draw, the drawing program. So it's loading Draw off the disk. And now the interesting thing about Draw is it has a totally different user interface from Bravo. Basically every program, they're developing their own user interfaces, they're inventing things as they go along. So you can see that Draw looks much more like a modern application. It has bars over on it has icons you can select. You can click to select what brush you want, what brush type. And now we can click to draw a round shape. We click 4 points. And then the paintbrush will draw a nice smooth curve through those points. We can draw more shapes. So by clicking the points and then doing the paintbrush, we can basically draw nice smooth curves. Let me try something a little more complicated here. So you can select a large number of points, and then it will draw a nice smooth curve through all those points. So so the nice thing about Draw is that you could then print it out on the laser printer, and because it's keeping track of the underlying points and the curve, it can draw it at high resolution. So you can print it out at much higher resolution than you see on the screen. They have user interface for doing transformations, but it's kind of a bizarre user interface. I'll just give a quick demo. The square box lets you select objects, and then the transformation triangle here lets you do a transformation. To do a transformation, you pick 3 points to make a triangle, and then you pick 3 new points to make a new triangle, and it computes the mapping between those 2 triangles, and then changes your shape. So it's basically a user interface designed by a mathematician. But fortunately, there's an undo operation, so you can undo it. And then something like the scissors, you might think is going to cut, but when we click, instead, it turns it into a dotted line. So they're really developing the user interface, and you can see the origins of a modern user interface, but there's still some things that are not the way they are today. Let me exit out of this. So the Draw program was used to make a lot of the illustrations that they put into the manual. You can come up later and I can show you what they look like in high resolution. So next I'm going to show SIL, which is the simple illustrator. And where Draw is designed for more of freehand drawing, SIL is designed for more of technical drawing. They'd use it for schematics and other technical things. So instead of letting you draw lines, it's more to draw boxes and lines. One of the interesting things about SIL is that it has macros built in. So you can define a very complex shape with a macro, and then just by hitting a key, I hit the A key here, and in a few moments it will draw an AND gate. So you can draw very complex things just by hitting a key. So this lets them build up complex schematics, complex diagrams. And so I'm going to load one of those now. Okay, so this diagram is rather complex, so it'll take a minute or two to load. But while it loads, I'm going to mention that one of the features of SIL is you could draw a schematic, and then they could take the schematic, feed it into an analysis program, and then feed it into another program. It would take the schematic, do analysis on it, it would generate a wire list, and then they could manufacture the board from that. So it was really, early electronic, CAD design and manufacturing. And so here you can see it's brought up a data sheet that they drew in SIL. So it's extremely complex, but because of the macros, it's relatively quick to draw even a complex thing like this with SIL. Okay, so let me clear that. And I'll load one more image into SIL here. So this, what it's loading is one of the diagrams from the hardware manual. So they would do the documentation for the hardware manual inside SIL. You saw this diagram earlier in Marc's presentation. So I'll quit out of here. And now what I'm going to do is switch disks and load the Smalltalk disk. So because the disks only hold 2.5 megabytes, you end up doing a fair amount of disk swapping in order to get the files you want. It was kind of limited capacity, and Smalltalk takes up a whole disk on its own. So right now I'm waiting for the disk to spin down before I can remove it. Okay, so I put in the Smalltalk disk. It now takes a minute, literally a minute, while it blows filtered air across the disk surface to clean off any contamination, and then it will load the heads onto the disk. And that way it makes sure there's no dust or anything that would cause a disk crash. So basically, the disk is spinning up. There's a door on the bottom of the disk where the air goes in. And then the air comes out where at the head opening. And so once it spins up, the heads will drop down onto the surface and the ready light will come on. And at that point, I'll boot up Smalltalk. Smalltalk was one of the very early object-oriented programming languages, and it was very influential in what happened later with C++ and Java. So it was highly influential. Okay, it looks like we're ready here. I'll hit the reboot button. The other thing about Smalltalk is it's where they did a lot of the modern GUI development. For the applications we've seen so far, it's only been one program running at a time, but I'll show you Smalltalk now. Okay, one thing about that does not look good. I've never seen the plaid effect with Smalltalk before. Let me try rebooting it one more time. Okay, it looks like there's something wrong with the Smalltalk disk, so I'm not going to demonstrate that right now, but perhaps you can come by our booth later if you want an up-close demo of Smalltalk.
Do you want me to bring the logic analyzer back?
Anyway, what Smalltalk gives you is much more of a modern desktop where you have overlapping windows. You can drag the windows around so you can have different applications in different windows. One of the other features of Smalltalk is that it lets you change the code on the fly. You can pull up any of the source code, modify it, recompile, and all while the system is running. So we have some debugging discussion back here that maybe we will be able to get Smalltalk running, so just hold on a minute. This is how you know it's a real demo, that it's a real system, so everything doesn't quite go as smoothly as you might expect. So,
I would say just go on to the games.
okay.
And just do
What,
way over time.
way over time? Okay.
And okay, we should also try to demonstrate key set.
Okay.
We'll go back to our original pack, which has a few games we wanted to show you. While it starts up, anybody has questions about the restoration or what we have seen so far? Okay, we either have made a terrible job or excellent job and everything's crystal clear. Oh, you don't have a question, you know all about it. Well, that was a question. So the question is, why did we put the CPU in front of the user knees? Because of course it's supposed to be on the side. And because we wanted to so there was a hot debate between the restoration team when we installed this. And they were the pro knees and the anti knees people. And we wanted to show it prominently. But that's right. In normal use, it would be off to the side, so you can set.
Okay, so I switched back to our first disk. This disk has some games on it.
Do you want to do the chord set? If you
Okay,
if you
but before that, I will show the.
Yeah, because we.
So I'm going to show how the chord set works. So this is just a keyboard test program. But
It's not plugged correctly.
Try.
There you go.
Okay.
So this is, we wanted to show it. It's a loan from DigiBarn. They are fairly rare. And this comes straight from SRI and Doug Engelbart. And we found really few programs that use it, but it's one of the innovations that didn't make it through. It's fun though. You can play Maze War with it. It works on Maze War.
Okay, now I'm starting up the pinball game. Writing games for the Alto was apparently a very popular thing, so we have a collection of games here. So in the pinball game here, you have the ball going around. They have a simple physics engine running it. So you can see the high resolution graphics that the Alto has. Oh, just lost the ball there, but you can see the flippers working. You might wonder how they got the ball to move so smoothly. The secret there is it's actually the cursor. They changed the cursor to be a round shape, and then they just move the cursor around. And the cursor is displayed. It's one of the very few things in the Alto that's actually done in hardware. So anyway, I'll move on from pinball. I'll now start asteroids. So this is your basic arcade-style asteroids game with the the spaceship and the rocks that you're trying to blow up and not hit. So it's looks like I just got blown up down in the bottom right corner. It's very hard to play while you're also using a microphone. But anyways, this shows that you're able to get on the Alto, fairly good movement of objects, even though you don't have a whole lot of processing power. The final game I'll show is sort of exhibits the how this was built in the 1970s. So this game is called Iran Wars, and it's a Space Wars game that was rethemed with the Iranian Revolution. So you have oil wells. Here's the Ayatollah going across the top. You have the American flags are being attacked. There's oil wells spewing oil. OPEC is there, and you get a mushroom cloud. So this, I'm not sure what the political message was supposed to be here, but it was clearly the 1979 revolution was impacting what was going on at Park. So let me exit from here. The first programming language for the Alto was BCPL, which was a predecessor of C. So I wanted to try writing some programs in BCPL. And so I thought an interesting thing to try would be Bitcoin mining. So I implemented the SHA-256 hashing algorithm. You can see it does about 2 hashes a second. Modern hardware will do about 2 billion hashes a second. So it's rather slow. I calculated that it would take about 5,000 times the age of the universe before it would successfully mine a Bitcoin block. So I'm not going to make my retirement off this. Oh, but wait, it succeeded. Look at that. The hash ends in a bunch of zeros, so it was a successful hash. Now the trick here is, of course, I just used a block that had been mined months ago, so I just knew where to start and it would succeed, so I didn't actually make any money off here. But it does show that the algorithm could actually have been running. They could have been doing Bitcoin in the 1970s if only they had thought of it. And so now to end here, I wrote a program to display a bitmap. And so this is basically a self-portrait of the Alto. It's just loading the image off the disk. And here you see the Alto drawing an Alto. So there you go. Thank you.
I think we are right on time, so I think we should, maybe you want to launch your the fractal, where we do that. And we would like to invite the next panel on stage. It will take us 2 or 3 minutes to get set up, and we'll be smack on time. So please stick around for the Xerox alumni panel and to ask all kind of questions to the guys that actually designed the machine.